that was all pretty straightforward because we assumed that f was constant. But I did kind of foreshadow the idea that it might get more complicated if we allow f to vary with latitude. And we really do need to do that because a lot of important dynamical phenomena depend on f varying with latitude. Rossby waves, for example, as you know from last year, right? On an f-plane, the geostrophic flow is strictly non-divergent, but on a planet where you have curvature to the surface of the Earth, right, you say that this geostrophic stream function, it contains f, right? So if f is not a constant, then it's not really a proper stream function for the geostrophic flow, this h, right? Which is going to have distortions, which is associated with divergent geostrophic flow. So what we're going to do is we're just going to say, well, this is complicated now. We can't just separate the geostrophic flow and the divergent flow. We have to say, well, there's the geostrophic non-divergent flow, which is the geostrophic flow you would have if f was constant. And there's everything else, right? The divergent part. And we're going to say everything else is small compared to this. Right? And that way we can actually include variations of f in our theory. And what we're going to do is derive the quasi-geostrophic equation set a little bit more formally than what we just did. Right? What we did just before was to say, well, let's get the equations. That term can be geostrophic, maybe not that one. Let's see what happens, right? This time we're going to expand, do a formal expansion about a small parameter. And that small parameter is, well, what is it that's small when you're close to geostrophy? It's the Rossby number, okay? So we're going to use the Rossby number as a small parameter, okay, and derive the quasi-geostrophic equation set. So this is where we get really serious now. Let's just go back to the full momentum equation, and this time I've just bundled the two horizontal momentum equations into a vector equation here. So v, bold faces, is the horizontal flow vector, okay? So d by dt of v plus v dot grad v, it's a bit abusive in terms of notation, but it just means the advection of the horizontal flow by the horizontal flow. This is the Coriolis term, the two Coriolis terms. So basically we're just writing two equations here as one equation. Here's the pressure gradient, and here's the continuity equation in divergence form. So you have dh by dt plus the advection of h and the h times the divergence. So there's no approximations there. That's the full shallow water set. And we're going to, first of all, non-dimensionalize those equations, right? So we're going to take typical scaling values of length, speed, and time, big L, big U, and big T, okay? And we're going to say this non-dimensional coordinate x prime is x over big L, etc. And we're going to also non-dimensionalize variations in the layer thickness by big delta H, which is whatever a typical variation in the layer thickness is. It's not big H, it's just a typical variation. Right? And remember that full H is big H plus delta H. So then if you do that, you substitute these non-dimensional numbers into here, you get something which is a bit more messy, because you've got all these scaling values sort of hanging around in front of the terms, and you've got these primes on these non-dimensional terms. The advantage now is that we know that we've non-dimensionalized, so these v prime and eta prime, we know they're order 1, okay, because they are compared with typical values. So far, again, there's no assumptions been made, no approximations. This is the full shallow water set. What we're going to do now is to introduce this geostrophic, or quasi-geostrophic assumption into this. So we're going to say that the relationships between L, U, and T, and delta H correspond to something which is close to geostrophic, right? So it corresponds to something where FV is of the order of G delta H. So if we put in the typical scalings into that equation, we'll end up with an expression which tells us a value for delta H in terms of these other parameters, okay? And that, if we now define our Rossby number as U over FL, now we call it epsilon, small, right? And another small parameter epsilon t is the temporal Rossby number. It's 1 over f times t. So now we're going to say these two things are small, right? You can see that if speed is equal to distance over time, right, then these two small parameters are the same, yeah? What we'll end up doing is saying that they're the same. All right, I'll come back to that in a minute. So if we just drop the primes on all these equations, then this is our momentum equation. So far, still no approximations. We're just rewriting it with this notation, this epsilon notation, okay? We haven't done anything where we impose the fact that that's small yet, but we will, okay? So there's our momentum equation, ready for treatment. And so let's do the same thing for the continuity equation. And you end up with this. If you put in all that scaling analysis, this temporal Rossby number times that thing in the brackets times d eta by dt plus the Rossby number times the same thing in the brackets times the rest of it. That's our continuity equation. And this thing in the brackets, L squared F squared over GH, is the inverse of the Berger number, which I talked about last week. Right? The Berger number is the number which, when it's of order 1, that means that Coriolis terms and gravity buoyancy effects are comparable, or that you can say that vorticity advection and vortex stretching are equally important. This Berger number is something which if it's of order 1, then we are dealing with typical synoptic systems which can be amenable to quasi geostrophic analysis. And it's also associated with the length scale. So the Berger number to the -1 is L squared over the Rossby radius squared, okay? The Rossby radius is that very important length scale that I was talking about last week. So we'll call it F, all right? So we can just put it in our equation there, F. Still haven't made any approximations yet. We can already see from these two equations that the zero order in our Rossby number, so if you just ignore these terms which are multiplied by the Rossby numbers, all you've got left is this fact that the flow is non-divergent, right? So geostrophic flow is non-divergent, or at least the zero-order flow is non-divergent, I should say. The first-order terms concern advection, divergence, and time development. Now, what we're going to do is do a formal expansion in the Rossby number, right? But first of all, let's just set out all our assumptions one by one, so we're clear about it. Assumption number 1, Rossby number is small, right? We're close to geostrophy. Assumption number 2, the temporal Rossby number is also small. And in fact, we're going to say that it's equal to the Rossby number. And as I hinted at before, what that means is that our scaling for velocity is consistent with our scaling for length and time. That means that our velocity is just the flow velocity. It's not some wave velocity which could go much faster. So what we've done here by assuming this is we've eliminated very fast surface gravity waves. We've eliminated tides, for example, which can go very, very fast. Buoyancy, gravity, stratification effects are as important as the Coriolis effect. So we're assuming now that length scale is close to the Rossby radius, or our F in our equations is the order 1, right? The consequence of assumption 3 and assumption 1 is that our departures from standard layer thickness are small. This is the linearization of the continuity equation and of the quasi geostrophic potential vorticity. This is equivalent to saying that the Brunt-Weissler frequency squared n squared varies in the vertical but not in the horizontal. Right? So I make a few references to the continuously stratified case, but we're going to stay in the shallow water framework. Assumption number 4, scales of motion are small compared to the radius of the Earth. Right? So L over the radius of the Earth is much less than 1. In fact, we're going to assume that it's the same as the Rossby number. So we just have one small parameter here, epsilon. So assumptions 3 and 4 got nothing to do with geostrophy. They're not something we would have guessed from the outset, that we're going to invent a system which is almost but not quite geostrophic. We wouldn't have guessed that you have to make these assumptions about the stratification or about the scale compared to the planet you're on. but they're necessary for what follows to be self-consistent. Let's talk about the beta effect, that last assumption that the length scales are small compared to the radius of the planet. Just basically means that the variation in f is non-zero but small, right? As you go north and south on your scale on your dynamical scale that you've chosen, right? So f is 2 omega times the sine of the latitude. If we do a Taylor expansion about the reference latitude phi naught, then you could say f is f naught plus beta y, you know this, okay? Formally, f is equal to f naught plus df by dy at the reference latitude times y, plus d squared f by dy squared at the reference latitude times y squared over 2, etc. That's our Taylor expansion. Of course, we only keep the first order term, and you can write it non-dimensionally as beta prime, which is this beta naught divided by f naught times L over the radius of the Earth. And that is just equal to the cotangent of the latitude, which is of order 1. You can't get too close to the equator because that's where cotangent of the latitude goes to infinity. So it's an extratropical beta approximation. After that non-dimensionalization, we can write f over f naught is equal to 1 plus epsilon beta prime y prime. So there you have it. You have that small parameter in front of the beta term, where you have this variation with latitude of the Coriolis parameter. So we're going to drop primes on y and beta. A quick note on the way people talk about this. But this is the f plane, okay? F is constant. If f equals f naught, then you're on an f plane. And that's all straightforward enough. It's just a constant value, right? People often refer to this as the beta plane. And what they mean when they say that is that the function for f in xy space is a linear function, right? So it's a plane in xy space, but it's only a plane in functional space, right? So don't confuse that with the shape of the surface of the Earth. What this specifically means is that the shape of the surface of the Earth is not a plane, it's a curve, right? It's because if the surface of the Earth was a plane, then f would not vary, right? So that's just something you want to make sure you don't get confused about. Beta plane is only in functional space, not in physical space, right? Let's get on with it. Let's do the expansion. So our equations are all non-dimensional. We'll expand the variables in increasing powers of epsilon. So here, recap, here are our two equations. They look a little bit more messy than they did before, but basically we've got some terms which are multiplied by epsilon and some which are not, right? There's our momentum equations and here's our continuity equation. And what we're going to do is take our variables, so we have three variables, u, v, and eta, eta being the departure of the layer thickness from its standard value, and we're going to write them down as a standard zero order part plus epsilon times a first order part plus epsilon squared times a second order part, etc. Right? So we'll take those variables and substitute them into these equations, and you get lots of terms, right? And then you just have to sort it out. You have to, you're going to find that this v naught, okay, in this term is just going to be zero order. It's not going to have an epsilon in front of it. But this v naught in this term will have an epsilon in front of it, so it'll be first order, right? Whereas this epsilon v1 term, even in this term, it'll be first order. In this term, it'll be second order, okay? So then we can just sort out what comes out of this substitution in increasing orders of epsilon. So we can start with zero order, so you don't see epsilon, that's zero order. And at zero order, it's pretty trivial, actually. At zero order, you have geostrophic balance. Big surprise, right? And in fact, that's the momentum equations that give you geostrophic balance. The continuity equation will just give you this term here. It's non-divergent. And in fact, the two equations are equivalent. There's no development, and the geostrophic non-divergent flow can only change with time if you add in some first order terms, right? This equation here basically is the same as this equation here, right? Do a substitution and you'll see that. So, one thing we can say though is that this eta naught is a useful thing to consider, because it will give us a stream function for the geostrophic flow, or for this, no, I should say for the zero order flow. So eta naught is a stream function for the non-divergent zero order flow U naught and V naught. Right? This doesn't represent the geostrophic flow now, it represents the part of the geostrophic flow which you would have if F was constant. All right, how about first order? This is where it gets interesting. This is what's left over when you've taken the terms which have just epsilon in front of them, not no epsilon and not epsilon squared, just epsilon in front of them. In the second equation, this term is 0, because this zero order flow is perpendicular to the gradient of the stream function of the zero order flow, and it's non-divergent. So this whole thing disappears. Right? And that leads to this equation. It's just that the rate of change of our zero order layer thickness is given by the divergence of the first order flow. The first equation, we'll take the curl of it. So when I cross differentiate, I take the two momentum equations, I do d by dx of one of them, d by dy of the other one, and I subtract one from the other. That's equivalent to just taking that vector equation and taking the curl of it, right? And that gives us an equation for the curl of the velocity, which is an equation for the vorticity, because the vorticity is the curl of the velocity, right? So here's our vorticity equation, and what can we cross out on this equation? This term is 0 because it's non-divergent. The zero order flow is non-divergent, and this term also can cross out because of the same reason, that the zero order flow is non-divergent. So if you combine this equation now with this equation, the continuity equation, you'll end up with this, right? You have something here which is equal to the divergence of the first order flow, something here which also is, okay? So just as we did before, you can eliminate the first order divergence and you can equate these two terms, and you end up with a conservation principle. Here we have it, d by dt plus v naught dot grad, so that's our substantial derivative applied to this quantity, beta y plus psi naught minus f eta naught, this quantity here, is equal to 0. So what that means is that this quantity here is conserved. Following the flow, this quantity here is conserved. And what is this quantity here? It's the same as before. It's the quasi-geostrophic potential vorticity. Here it is again, this equation. It's an equation for the conservation of quasi-geostrophic potential vorticity. You can express it, you can express this substantial derivative in terms of the stream function eta if you want, and you can express this potential vorticity also in terms of the stream function eta. Remember that the vorticity is the Laplacian of the stream function, okay? So that just gives us that in terms of eta. The stream function will give the advecting flow, so you can write that in terms of the stream function. And so everything is in terms of the stream function, eta, if you want. So that is just an expression of conservation of quasi-geostrophic potential vorticity, Q. And you can write it like this as well, dq by dt equals j eta naught q. J is the Jacobian. It's just a compact way of expressing advection when you have a non-divergent flow in terms of the stream function and the quantity that is being advected. Okay? So Jacobian is d1 by dx plus d the other by dy minus the same thing the other way around. That's a Jacobian. Okay? So you can write j stream function tracer is equal to the advection of the tracer by the non-divergent flow. What we learn from this is that we have just one variable in this system now. Right? We had the shallow water equations, you needed three variables. Right? You needed u, v, and h. Right? Now we can express everything in terms of eta. One equation, one variable. Our one equation is this. It's the conservation equation for quasi-geostrophic potential vorticity, right? Our variable is eta, because Q can be expressed entirely in terms of eta. So we're down to one equation and one variable, which is a useful thing if you're going to do weather prediction, okay? Now this is all still a bit obscure because it's all non-dimensional, right? So what we'll do now is put the physical values back in. We just do the opposite of what we did when we non-dimensionalized these variables. We redimensionalize them, okay? And you get this. So the dimensional quasi-geostrophic potential vorticity is beta y plus the Laplacian of the stream function minus f naught over h times delta h, okay? So there's our beta term, our relative vorticity, and our vortex stretching term, if you like. You can also express it like this, 1 over the Rossby radius squared, and you can express the conservation as before. And you can, if you want, you can put f in there as well. You can say that q is equal to f plus beta y, or f naught plus beta y. You can do that. It doesn't make any difference because f naught is a constant, right? So if you put it in here, it doesn't make any difference. So either definition of Q is all right. I'll just talk about the extension to more realistic fluids. Because so far we've been using the shallow water equations, been using just one shallow water layer. What if you want an atmosphere where you have, or an ocean, where you have more realistic variations of density with the vertical and with the horizontal? You still have a concept of quasi-geostrophic flow. You can still write an equation for the conservation of quasi-geostrophic potential vorticity. It's exactly the same. What changes is the definition of Q. So in a fully stratified flow, or in a flow where the stratification varies with the vertical, and in which also the Coriolis parameter varies with latitude, you define your stream function now in terms of the pressure and F naught. Okay, so the stream function is now the stream function just for the non-divergent part of the geostrophic flow. And we can talk about how our density varies in the vertical and the horizontal. We say that there is some reference value of density, which can be a function of height, and a perturbation, which is a function of x, y, z, and t. So this is the anelastic approximation. Okay, so quite realistic. And you can do the same kind of expansion in small parameters in terms of the Rossby number and get the full quasi-geostrophic equation set out of that, and you'll end up with this as your definition of potential vorticity. So it's the same as before. You have beta y, you have relative vorticity, and you have something that depends on vertical gradients of the stream function. It's a bit more complicated. You have d by dz of this times d psi by dz. Right? You can make it a little bit simpler if you, instead of using the anelastic approximation, you just say this rho s is constant. That's the Boussinesq approximation, and then you end up eliminating this density variable between these derivatives, and you end up with something a bit more straightforward. And this is a very useful, very well-known form for the quasi-geostrophic potential vorticity. If you want to know the derivation of these equations, they're not part of the course, but we've got some light blue transparencies coming up, and they give you everything that you need to know to understand that fully, those derivations. Okay. So there's 3 pages of algebra, four pages of algebra that you are never, ever going to look at. Well, maybe you are. I mean, if you're really into it, then you know, I'd be delighted. So what do we get from all this? We get one variable to rule them all, and it's a very useful thing, this quasi-geostrophic stream function. Everything can be expressed in terms of psi, the stream function in a quasi-geostrophic set. Obviously, the horizontal velocity can be expressed in terms of the stream function, right? That's definition of the stream function. Also, the pressure is just is the stream function, really. Pressure is the stream function for the non-divergent geostrophic flow. The density is the vertical gradient of the stream function. And even the vertical velocity is a material tendency operator applied to the density. So you can get everything out of the stream function in a quasi geostrophic set. The other thing you can do with the quasi geostrophic set is make predictions. All right? So what's the procedure? So let's say you know what the flow is at your initial condition. This is the weather today. You can work out Q, because you know the definition of Q, right? So you can calculate it, okay? And you can have a three-dimensional field of Q, right? A potential vorticity map. And then you can work out the advection terms, and so how Q is going to change because it's being blown around by the wind, okay? Q is conserved following the flow. If you step that forward in time, you will have the next state for Q. So, time step plus 1, which could be a few minutes later or half an hour later. You can go quite long on the time steps with a quasi-geostrophic set because you have nothing really fast going on. You don't have gravity waves. Okay? So you go forward one time step, half an hour, and you've got a new value of Q. You can then invert that. So you take this definition of Q and you do an inverse problem to find out what the stream function is. Okay? And you've got a new flow field. And then you start again. You go round again and step forward another half hour. Right? And you do that 48 times, you've got the weather tomorrow. Okay? So that's your prediction system. As the first weather predictions were done with the quasi-geostrophic set.